Team, let's talk about electric fields. I think it was important. We talked a little bit about it in my last video, and I hope that you saw it, but I'm going to do this problem just in case you have any other questions on electric fields. So let's start off with identifying what exactly it's asking us. It is asking us to find the electric field at the lower right-hand corner right here, and I'm going to put a reference point. I'm going to put a reference point here of the square shown below. So we have three charges. 1, 2, 3. Electric field doesn't mean that it's actually experiencing any force. It means that it has the potential to experience force if you put a charge at this point right here. Like, what would the force be and what is the direction of that force if you put a charge there? However, we're not actually analyzing force. We're analyzing what is the electric field that is created by these charges here, that if we do put a charge, what would happen to it? So to clarify that, we do this imaginary lines to denote the electric field, and we put in a system where when we find a positive charge, like for example this one, we understand that the electric fields for a positive charge are going outwards of the particle, the charge, outwards of the particle. So go this way, that way, this way. But we're only focused on the reference point. So the electric field pointing downwards is the thing that we care about, not the others. Okay? Only the direct line that is pointing at the reference field or the reference point. Okay? So we understand that this particle right here is pointing directly at the reference point. Then we have another charge, another positive charge around here, where we do the same because it is going outwards of the charge. We're pointing it directly into the reference point because that's an experience. Again, like the electric fields go everywhere outside of outwards out the charge, but the one that we care about is the charge, the electric field that is hitting straight into that reference point right here. Finally, we have the negative charge. So the negative charge is a little bit different from the positive just because the line itself, it is inwards into the electric field. Inwards into the electric charge. It is an electron, it's going inwards. So from the reference point. So we have electric field here, electric field here, an electric field here, electric field here, such and such. But the only one that we care about is the one that directly ties to the reference point. So I'm going to erase all the other electric fields so we don't get confused. Okay, now we have our vector notation. So let's put in that we are writing down a coordinate axis, y and x. Because when it comes to electric fields, we're dealing with vectors. Don't get lost in this. I know that you're not used to the vectors moving, but vectors can be moved as long as you maintain the same direction and the same magnitude. So I can rearrange this. This is my reference point. Again, I can rearrange this by moving this right here. Moving my coordinate or my negative one right here. And by moving, still this one, like this. You don't have to do this. As long as you know where the X and the Y are, you don't have to do this. This is just to make you see or have you see like it is exactly a part of the X-axis or the coordinate axis, and we can definitely apply and studying electric fields in both the X and the Y direction. But just as long as you know that this is going downwards with respect to the coordinate axis, so that means in the Y direction this is negative, this is going over here, this is going in the positive X direction with respect to your coordinate axis, and this has an angle, and it is both acting in the X and the Y direction, then you should be fine. Okay? Now, one thing that I want you to notice is that this is a isosceles triangle, or at least this is an or a cube or a complete square. But if you do a line from here to here, it becomes an isosceles triangle. In an isosceles triangle, you have an angle of 45 degrees that is created here, and then another angle of 45 degrees here. I am just going to focus on this angle of 45 degrees right there. So electric field, and I kind of missed this, but physics is equal to, and it's also asking for what is the force on a charged Q placed at that point. Okay, so let's write down all the equations for electric fields, and let's go to our PRC. PRC, where are you? All right, PRC, electric fields. Okay, so we have these two equations, and I'm going to copy paste them that I know that I'm going to need later on. Copy, paste, boom. So I have my equations for the electric field. So the first one, actually, this is electrostatic force, but you're going to get it because we're going to need it later on in B. So this one is the one that we need right now. It says the vector of electric field is equal to the permittivity of free space, or no, not permittivity, sorry, Coulomb's constant, blah, I messed that up, Coulomb's constant, K, times the charge, an absolute value, times r squared, the distance from the reference point, from the charge to the reference point. The distance from the charge to the reference point. The distance from the charge to the reference point. And then the distance from the charge to the reference point. I am letting you know that because it's extremely important what's going to happen next. So now that we identify the direction, we identify the angle, and we have identified the electric fields, and I'm going to denote this as electric field 1, electric field 2, and electric field 3. Let's find all this, the net electric field in the X direction. And the net electric field in the X direction is going to be, first, E1, which is being affected by this positive charge, and that is positive. But for when it comes to E3, electric field 3, it is being affected in the negative direction of my X coordinate. So E3 cosine theta to get the trigonometric function, the component in the X direction for E3. Okay, so those are the only electrostatic fields that are acting on the in the x direction. So we can replace this as the charge in E1 is Q, K, that's positive, A squared, because this is A, this is a distance A, minus K, absolute value of 2Q over 2, 2Q, that's all. Right? See, 2Q right here. All right, fantastic. Over the distance from the reference point to the charge of negative 2Q. So you can do the Pythagorean theorem where you're trying to solve for the hypotenuse here, and that would give you a squared plus a squared. See, a squared, and that is going to be a square root of 2. It's going to give you a square root of 2. Plug that in, a square root of 2 to the power of 2, because it is going back to the radius, or not the radius, but to the distance from the reference point. And then you multiply cosine of 45, because you want the component in the x direction for E3. And voila, you are done with the x direction. You simplify it, and once you simplify it, I'll do it. I was going to not do it, but I guess I'll do it. KQ A squared, parenthesis, I just took everything off. Cosine of 45 is square root of 2 over 2. And I am left with 1 minus, oh man, did I do this right? That's how much I don't want to do the either. Okay, so just simplify it. I am not going to simplify it for you. You get the gist, and you get to this point. Now let's go to E, to the electric field in the y direction. The electric field in the y direction is, now we're talking about E2. So E2 is going downwards. So E2 is negative because it is going downwards. See the arrow right here? It's going downwards. And then we have E3, but E3 in the y direction is going positive. E3 in the y direction is going positive, but this time, since we want the component in the y direction, we go sine of 45. And sine of 45 is also the square root of 2 over 2. So we continue working at it. So now we are going to negative k, the absolute value of q, over a squared, plus k, negative 2q, over a squared sine of 45. Okay, all right. So now you basically can solve for this again, simplify this as much as you can, and you have, give me a second, square root of 2 over 2. So this is important because now you have basically the electric field in vector notation for the reference point in P. So E x I plus E electric field in the y direction, J. Plug these in. And you should have the answer for electric field. Okay? One thing that you can do is, it's important to leave it just as it is, because now the way that you work it is that it's asking you for what is the force on the charge Q placed at that point. We have found the electric field at the reference point. The only thing that we need to do now is literally rewrite the equation that we have here and add that charge Q into our electric field. And notice too that because of our unit vector notation right here, since we have the direction, not the magnitude, but the direction and the x and y components of the electric fields, we also now can get the x and y components of the force, and that means that we can analyze the magnitude and direction of that force as well. So basically, once we analyze the electric field, it was just a matter of putting a charge in there to identify that the force being applied, being experienced on that charge in the reference point. And you are done with the electric field concept. I hope this class was good for you. I hope that I explained it decent enough. And if you have any questions, let me know. Email me. You know who I am. So take care. Have fun. And I'll do another video soon. Bye-bye.